Our intuition is that we can use about log n multiplications to compute x to the n if we're clever with how we kind of propagate our partial answers through. So let's formalize this and let's actually figure out what's going on here. So here's the mathematical idea behind what we're trying to do. This is a mathematical formula that holds for any x and n. So if I write x to the n, what we've just observed is an instance of the fact that I can rewrite x to the n in the following way. I can write it as x squared to the power of n over 2. So why is that? Well, if I ever have, this is the rule, right? Here's a law of exponents, that if I ever have a to the b to the power of c, this is equal to, right, by definition, this is equal to a to the power of b times c, right? If I raise something that's to a power, then I can put them all under one power that is the product of those two powers, right? And so I have this fact, and so all I've done here is observe that I could split n into 2 times n over 2, right? This is just true because n equals n over 2 times, I won't use x, I'll use the dot because I've got an x somewhere else, times 2, right? This is just a basic algebraic manipulation. So if I have this formula, x to the n can be written as x squared to some exponent, then I can use that to build an algorithm. And so now I'm going to make a gross simplification that'll make our algorithm look, it'll make our algorithm look prettier, it'll make the analysis go through more easily. It actually won't change any of the technical results that I give you, but it will be much, much, much less confusing. So we'll go into some detail about when you're allowed to do this and when you're not allowed to do this at some point, but for now, let me just make the following assumption. Right, so my assumption is going to be on n, my assumption will be that n is a power of 2. So n equals 2 to the k, where k is greater than or equal to 0 and an integer. Okay, so why am I making this assumption? Well, what I'm going to be doing is I'll be taking this formula and I'll be saying, I'm going to evaluate x squared to the n over 2, and I want to guarantee that when I do this repeatedly, my n over 2 will always be an integer. Right? I always want to be dealing with integer multiplication, and so I want to make sure that n over 2 is always an integer. So, if n equals 2 to the k, then n divided by 2 is an integer, right? So this equals 2 to the k over 2, which is just 2 to the k minus 1. Right? This is just, by the definition of exponentiation, this is equal to 2 to the k minus 1. So that means if this is a power, if n is a power of 2, then so is n over 2, and so is n over 4, and so is n over 8, and so on. Right? So by assuming that it's a power of 2, I'm just going to guarantee that this is always an integer. All right. So what's my algorithm? Well, here's some pseudocode that does what we want to do, and then I'll explain how this is working and why this is the right thing to do. So I'm going to call this exponentiation by squaring. Right? And this is the name of the algorithm, exponentiation by squaring, if you want to go look it up. There may be some issues with the Wikipedia page, just to warn you, but maybe you can find a different resource as well. Takes in two arguments, x and n. And this is the simplified version that assumes that n is a power of 2. And so our base case gets to be very simple, right? We say, suppose n equals 1. Right? What happens if n is 1? Then we're trying to compute x to the power of 1, which is just x. Right? So we just return x. Return x. And if it wasn't clear, we're going to do this in a recursive way. Right? This formula above suggests a recursive approach, so we're gonna program this in a recursive way. So if n is 1, then return x. Otherwise, what do we return? Well, we just return something that's based on this formula up here. So we return exponentiation by squaring, right? A recursive call, exp squaring. of what? Well, what we've said is we're going to rewrite x to the n as x squared to the n over 2. So we just plug those numbers in, right? We pass it x squared as its argument for x. So x squared, and for its exponent, we pass it n divided by 2. Right? And we are guaranteed that n divided by 2 is a power of 2. Right? We're also guaranteed that if we recurse a number of times, eventually n over 2, getting cut in half a bunch of times, because it's a power of 2, eventually that will be 1, and it'll hit our base case right on the nose. Right? So we are guaranteed that this algorithm will terminate, and as long as we believe this formula up here, we're guaranteed that it will return the correct answer. Okay? So let's analyze this. This is a fairly simple recursive algorithm, and so we'll use a recurrence relation to analyze it. But what recurrence relation will that be? So what we do to analyze this is we'll say, hey, this is our t of n, right? When I call exponentiation by squaring the first time with n as its input, then it will perform a certain number of basic operations, right? It'll perform a certain number of multiplications to do its job. I don't know what those are yet, but that's what it is, right? When I call it, I'll get this many. So what I'll do is I'll say t of n equals, and then I will ignore everything here in the base case because I know that's stuff that isn't going to happen every single time. And then I'll look at the place where my multiplication occurs. Right? Where does multiplication occur? It occurs here when we compute x squared, right? X times x is our multiplication. So that means when this line comes and I make a recursive call, I get one multiplication, right? So that 1 there is the multiplication of x by x, okay? And then I also get a recursive call. So this is where the recursive piece of the recurrence relation gets defined. So here I'm saying, what we have is one multiplication and one recursive call with n, with its argument, equaling n divided by 2, right? With half the value of the exponent that we started with. So 1 plus t of n over 2. So remember, what does t of n signify? T of n signifies the number of multiplications that we have to perform if the exponent is n. And so what are we doing? Well, we're saying that number is 1, right? A multiplication plus however many multiplications it takes to compute x, to exponentiate with an exponent of n over 2. So we cut the value of the exponent in half and perform a multiplication. And that's what this recurrence relation is saying. So put them together and we end up with t of n equals t of n over 2 plus 1. Right? And that's our recurrence relation. This is it. Right? So here is another example. We've done this now for Tower of Hanoi. We did this for the Fibonacci sequence. And now we've done this for exponentiation by squaring. We've seen how you can go from pseudocode to a recurrence relation, and then if you don't remember what the actual value or what the complexity class of this recurrence relation is, work it out for yourself. Right? Like literally right now, pause the video, get a piece of paper, and figure this thing out. You've just finished the big homework on recurrence relations, so you should be pretty comfortable with this stuff. Work it out for yourself. Look it up in the video if you can't figure out how to do this. We've actually already done this recurrence relation. And then by now, hopefully you've worked it out for yourself and convinced yourself that this is big theta of log n. Right, so this is the log n complexity class recurrence relation, which makes sense, right? We're cutting our input size in half, or technically speaking, we're cutting our input value in half here. And performing a constant amount of work to do so at each step. So this validates our intuition that we had developed earlier, that we can exponentiate to a power of n with about log n multiplications. And now we actually have a little bit of math to back that up, right? We actually have some rigor behind our intuition. So real quick, before I wrap this up, I just want to mention one thing. You may be looking at this and saying, why are we saying only one multiplication here? You know, isn't this sort of like a multiplication? Don't we kind of have two? And in some sense, you're right. There is, you know, we're taking x times x, and then we're doing this division thing with n. And so, yeah, there's more work that's happening here. Technically speaking, there's more work that's happening here than just a multiplication. But the reality is the answer here doesn't depend on that level of detail. So there's actually 2 points that are worth pointing out here. One is an architecture point, essentially, and that's that n over 2, right? If n is an integer, dividing it by 2 is essentially just a right shift of that integer, right? Dividing by 2 is a right shift, multiplying by 2 is a left shift, because these integers are all going to be represented in binary in the computer. So that is a much, I mean, an order of magnitude or several orders of magnitude faster operation than multiplying two arbitrary numbers together. So on the one hand, right, the first part of the answer as to why we don't have to care about this piece is that it's negligible, right? Dividing n by 2 is a negligible operation. It is extremely fast compared to taking x and multiplying it by x. So that's point number one. But point number two is that I don't even care, right? Suppose you're really, really hung up on this idea that, hey, there's more work happening here than just x squared. Then what I will do is I will say, hey, look, all this is constant in the size of n, right? If n is stored in a register somewhere, shifting it doesn't depend on the value. It's a shift either way. And so what we have here is a bunch of junk, right? I can just call this junk that doesn't depend on the size of n, or at least doesn't depend on the value of n. And so then rather than representing my recurrence relation as the number of multiplications that get performed, I can just represent it as the amount of junk that gets performed. And I'm being serious, right? I mean, junk is not a technical term here, but whatever it is that I call this piece that's underlined in green, that's what my recurrence relation is capturing. It happens that in reality, the x squared will dominate this, but I don't even care about that. All I care about it is that it's constant in the value of n. And so this is what we're capturing here. If you like, you can think of, you know, this entire line as being the basic operation. Right now I've given myself a mustache. You can think of this entire line as being the algorithm's basic operation. But you know, in any case, the exact amount of time it takes to do that isn't what matters. It's how the number of calls of that changes as we change the size of n. So that wraps up today's set of videos. I strongly encourage you to go and read the brute force chapter, particularly read the beginning of it where it talks about sorting algorithms. Get familiar with the elementary sorting algorithms so that in the coming weeks when we start talking about more complicated ones like merge sort and quick sort, you'll be prepared with kind of a basic knowledge of how sorting works. So go read the chapter, and I'll see you very shortly in the synchronous session.